Good morning, everyone. So today we are going to see the estimation of line size for various unit operations involved in pharmaceutical industry, and we are going to explain this particular case using two scenarios. The first scenario is going to be for the utility, and the second scenario is going to be for a specific reagent addition. So before going into the topic, so we need to brush up certain basics, and we need to have some clarity on the calculation part. The the line sizing is majorly depends on the volumetric flow rate and the velocity. If these two things are known, then automatically we can estimate the line size using the formula. So capital V. So this is the volumetric flow rate, which is nothing but the product of cross-sectional area and the velocity, which is represented by small v. So using this formula, we can calculate the line size. And the velocity is going to change from fluid to fluid. So if it's a gas, so the velocity is going to be high, and if it's a liquid, the velocity is going to be low. And within the liquids itself, so it is going to vary, and we are going to see how it is going to change. So I have collected certain velocities of fluids depending upon their nature. And before going into the topic, we need to see certain kind of basic things like exactly how a fluid is going to flow. So let's say this is a tube, and within this tube, a fluid is flowing, and usually fluids are going to flow as layers. Like in multiple layers, the fluid is going to flow. So let's consider this as a streams inside the fluid. So these arrows indicates the flowability or the flowing of a layers inside the tube, and the surface of this tube is nothing but a skin. So the flow stream which is being flown over the tube surface is going to have certain type of resistance which is being offered by the skin, and this is nothing but a skin friction. Similarly, the layers which are being flown above this basic flow stream is going to be offered with some kind of a resistance which is nothing but a form friction. Form friction means the friction which is being offered, like the friction which is being offered by the neighboring streams. So this form friction is going to be very low compared to the skin friction, and this skin friction is going to vary from fluid to fluid depending upon the liquid's viscosity. If the viscosity is high, automatically the friction is going to be high. If the viscosity is low, then automatically the velocity is going to be high. And let's try to write up all these velocities of liquids. So some of the velocities are being defined based on the rule of thumb, and some of the velocities you have gathered based on our practical experience. So first thing is, if the fluid is viscous, the velocity is going to vary between 0.6 to 0.9 meter per second. If the fluid is non-viscous, so this is going to vary between 1.2 to 1.6 meter per second. And if it's an organic mass, like let's say whenever you are going to pump a reaction mass, then in that case you can take the velocity between 1 to 1.2 meter per second. And if it's any kind of solvent, then we should restrict the velocity to 1.2 meter per second. Why? Because if the velocity is high, automatically there is a risk due to static generation. And if it's a water and the line size is less than 2 inch, then automatically the velocity can be 1.2 to 1.8 meter per second. If it's for the same water and the line size is greater than 2 inch, so automatically the velocity varies between 2 to 2.5 meter per second. The reason for variation of the velocities with line sizes is, if the line size is low, automatically there will be less flow rate, and if the line size is high, automatically the flow rate is going to be high. And coming to utilities, so let's say it's a chilled water, so it's going to be between 1.5 to 1.8 meter per second. If it's a chilled brine, so it's almost 1.25 meter per second. And if it's a RT water, like the cooling tower water, so the velocity is going to be approx 2 meter per second. And if it's a hot water, so the velocity is going to vary between 2 to 2.5 meter per second. And if it's a saturated steam, so it is going to be vary between 25 to 30 meter per second. And if it's a superheated steam, then the velocity is going to vary between 50 to 80 meter per second. And now let's get into the topic where we want to calculate the line sizing for different scenarios. So the case that I am going to take is estimation of utility line size requirement for performing a reaction with heat liberation of 1500 kilojoule per kg of KSM, and the mapped batch size is 500 kgs. So this is the case, and we would like to calculate the utility line size requirement for this particular case. And first of all, we have to make a note of the inputs, like the heat liberation, which is identified as 1500 kilojoule per kg of KSM, and the batch size is going to be 500 kg. So total heat liberation, this is going to be the product of the batch size and the heat of reaction. This is going to be in kilojoules. And now let's convert this into kilocalories by dividing with 4.184. This is in kilocalorie. And the cooling capacity requirement, the cooling capacity requirement is going to be the total heat liberation divided by 3024. So this you are going to get in TR. And let's say the addition time, so here let's consider this is a semi-batch reaction and the addition time is almost 3 hours. So the cooling capacity requirement is going to be the total TR divided by the addition time. So this is going to be in TR per hour. And once this is known, so we should check the addition temperature also. Okay, the addition temperature, let's say this is at 0 degrees centigrade. The utility used, I'll be considering it as chilled brine, and the utility in temperature is going to be at minus 15 degrees centigrade, and the utility out is going to be approximate minus 11 degrees centigrade. I'm going to consider 4 degrees of delta T. So the delta T equals to 4 degrees here. And the specific heat of chill brine is, let's say, is approx 0.9 kilocalorie per kg degree centigrade. And now we need to perform the energy balance. So we know the cooling capacity required. So this is nothing but a demand from the process, and we are going to neutralize this using the available utility. So we are going to equate this cooling capacity requirement to the utility flow rate, and the utility supplied, it is nothing but a MCP delta T. So we need to perform energy balance by equating demand and supply. So the demand is 19.8 TR per hour, and the supply is going to be M, and the CP is 0.9, and the delta T is 4 degrees. So the mass flow rate is going to be M for the utility. So M equals to this divided by 0.9 multiplied with 4. This you are going to get So before converting this, let's try to convert this into kilocalories. So just multiplied with 3024, and here you got this in kgs per hour. So for the same, we need to convert this into volumetric flow rate. So to convert that, we need to divide this mass flow rate with the density. So coming to the densities of the chilled utilities. So I get a list here. If it's a chilled water, so the density is going to be approx 960 kg per meter cube. And if it's a chill brine, which is at minus 15 degrees centigrade, so the density is going to be almost 920 kg per meter cube. Why? Because we are going to mix methanol with the chilled water so that you can attain this minus 15 degrees centigrade without freezing, and the composition, so that you can back calculate using this density. And if it's a chill brine at minus 40 degrees centigrade, then it is going to be almost 860 kg per meter cube. So here we are going to use utility at minus 15 degrees. So I'll be taking the density of 920 kg per meter cube. So the volumetric flow rate, capital V, equals to this divided by this 920. So you got it in meter cube per hour. So I need approx 18 meter cube per hour. So as per this last discussion, the velocity of chill brine is going to be approx 1.25 meter per second. So first of all, let's try to convert this required volumetric flow rate into meter cube per second. So this is going to be 18 divided by 3600. So this is going to be in meter cube per second. Now let's divide this volumetric flow rate with the velocity. So you are going to get the cross-section area. This is in meter square. Okay, so after getting this cross-section area, the formula to calculate the line size is, so area equals to pi by 4 d square. So this is the formula, and we can rewrite this formula as d equals to a into 4 divided by pi to the power 0.5. So we can use the formula to calculate the line size. So the line size is equals to the cross section area multiplied with 4 divided by 3.141 to the power 0.5. So this is in meters, and let's convert this into inches. So by dividing it with, sorry, first of all you need to convert this into centimeters, that is into 100 divided by 2.54. So this is in inches. So to compensate or to neutralize the heat which is being generated during the reaction, so you should have minimum 3-inch line size. So this is approx 3 inches. So this is how you should calculate the line sizing required for a utility. So this is case 1, and the case 2 is going to be where you are going to dose a specific reagent into the reaction mass at 0 degrees centigrade in 3 hours of time. So I'll mention it, the case 2, where you are going to perform addition of reagent to mass at 0 degrees centigrade in 3 hours of time. Okay, first of all we need to take the volume of reagent. So let's say the volume of reagent is approx 180 liter. Now the next thing is the volumetric flow rate. So the volumetric flow rate is 180 divided by 3. So this you are going to get in liter per hour. So this is the volumetric flow rate. And let's convert this volumetric flow rate into meter cube per second. So to do that, so first of all divide this 60,000 to convert this into meter cube, and then divide the same with 3600. So this is going to be in meter cube per second. So coming to the reagent property, it's a viscous in nature. So usually the reagents are going to be slightly viscous in nature. So I am going to take the velocity of reagent as approx 0.8 meter per second. If the reagent velocity is 0.8 meter per second, so you already know the volumetric flow rate, then simply to calculate the cross-sectional area, so just divide the volumetric flow rate with the velocity. So you are going to get this in meter square. So apply the same formula to calculate the line size. So the line size is going to be this divided with, sorry, the cross-section area multiplied with 4 divided with 3.141 to the power 0.5. This is in meters. And now let's convert this meters into inches. Multiply with 100 divided by 2.54. So that means approx you got 0.2 inch. So if possible you can take up to either between 0.25 inch or 0.5 inch. And now the question is, if the line size increased, so automatically the velocity will increase. So automatically what will happen is Instead of completing in 3 hours, it might get complete in 2 hours. So just to control that, so we have to do the addition depending upon the temperature, or else you have to apply a valve inside the line. And also one more thing that need to be noted is, when the vessel, like the addition vessel, is full of reagent, that means the height of the reagent is more inside the vessel, automatically the flow will increase, and as the level is going to decrease, so automatically what will happen is the velocity is going to reduce. Okay, so this is how we are going to estimate the line sizes for different scenarios, so either for a process or for the utility. So hope you have enjoyed the video, and if you have any questions in this video, please reach us at pharmacalci823 at the rate gmail.com. So I'll be attaching this particular sheet in the description, and you will be having a downloading code of that, so try to download it if required. And if you like our content, please subscribe to our channel, and also please share it with your dear ones. So thanks for watching the video.